Okay, my name is Dan Nikpayuk. It's my talk, C++ is a metacompiler. So the outline for this talk, introduction, I'll just introduce myself quickly. Demonstration of what my project is very quickly. Philosophy, I just go over basic design. Methodology, just theoretical methods I use. Library, excuse me, I'm a little bit nervous. This is my first live talk, so bear with me, thank you. Okay, so library, that's the actual library. I'll go into implementation details. I'll still keep it fairly soft, but language, I'm going to give grammatical examples, but you'll understand what that means in a bit. Performance, everyone's interested in that. And a roadmap for future direction. Okay, introduction. Who am I? I'm a self-taught coder. I've been programming in C++ since 2005. I don't currently work in the tech industry. I have a Bachelor of Arts in math, majoring in math, minoring in economics. I'm Inuit, specifically Inuvialuk, from Canada's Western Arctic. I'm devoted to the continued renewal of my people's language and culture. Okay, so why C++? It's a life goal of mine to build a programming language for multimedia production. I hope to offer said language as an option for storytelling and retelling, telling and retelling my people's stories, traditional and new. Such a language will generally require systems level performance, and so C++ is a good fit for writing its first compiler. Okay, so what is a metacompiler? The philosophy section discusses this design. So here we show a few coded examples. Factorial, everyone's familiar with that. Okay, just give you a moment to just take that in. Okay, so we have a C++ 17 constexpr function. This function takes no input. This function returns source data. The source data is a string literal. And the string literal is sourced from another language. So this other source is a domain-specific language, and this DSL is an assembly-inspired language called Chord. Okay, so relevance. So it says the word metacompile, and there's that Chord factorial function. So in effect, we metacompile our DSL source code. We pass it as a template parameter. It returns a constexpr function. Okay, so here I'm computing 9 factorial as a static assert. So our metacompiled function can be used either at compile time or runtime. For those who want a bit more detail, metacompiler turns this into this, which we then pass to this. There's a lot of detail there, but effectively it's continuation passing function. And so all that combined finally turns into a constexpr function. But we're getting ahead of ourselves. Okay, so second example, factorial again. Okay, give you a moment to take this one in. Okay, so we have another C++ 17 constexpr function. This function also takes no input, and this function again returns source data. The source data embeds another string literal, and the string literal encodes source from yet another language. The source is again domain-specific language, and this DSL is a scheme or Lisp-inspired language called Hustle. Okay, finally, as with the Chord example, we can metacompile and apply this function as well. So onto the philosophy section. So C++ is a metacompiler. We've seen what a metacompiler does. We now ask what a metacompiler is. So let's take a short tour of related concepts. So we start by asking, what is a compiler? What is an interpreter? What is a transpiler? To keep things simple, a compiler takes source code and translates it into assembly. An interpreter takes source code, translates, then executes it directly. Transpiler takes source code and translates it into the source code of another language. So do these ideas apply to a metacompiler? With a compiler, yes, a metacompiler takes source code and translates into an intermediate assembly. An interpreter, maybe a metacompiled function can be executed at compile time. Transpiler, also maybe. Metacompiler takes source code and does translate it into C++, but only C++. So I've called it a metacompiler. What makes it meta? The prefix comes from metaprogramming. In C++, this means compile time programming. This includes constexpr time programming, as well as template metaprogramming. So as such, a metacompiler requires we refine our notion of time. We ask, what is a timescape? And what is a time scope? The short answer, when observing the lifespan of a program, a timescape allows us to decompose it into time scopes. As for specific time scopes, runtime is when a program is being executed. Compile time is when a program is being translated for execution. Meta runtime is when a metaprogram is being executed within the scope of compile time. Metacompile time is when a metaprogram is being translated for execution within the scope of compile time. Quick summary, visual. Okay, so what about constexpr time? This is C++ specific, as far as I know. It might be in C now, but this time scope in effect represents either runtime or meta runtime. Okay, so a metacompiler requires we also consider ideas of self-similarity. Why? Because in theory, we could metacompile source code from the same language that is otherwise being compiled. Given this, we ask, what is a metacircular evaluator? What is a self-hosting compiler? What is an abstract machine? And what is a virtual machine? So a metacircular evaluator starts with an interpreted language, builds a metacircular library, builds a function called an evaluator. This evaluator simulates the language's own interpreter, and this evaluator can execute source code from that same language. So a self-hosting compiler is the compiled version of a metacircular evaluator. What's the difference? An interpreter is allowed to interleave source code translation with execution. A compiler is restricted to modularizing source code translation and execution. It must translate first, and only then can it execute. This creates subtle differences in their respective designs. Okay, abstract machine is a state machine. It performs computations by passing data through a chain of states. Such states are usually expected to have the same shape. In effect, you can consider them to be a data structure. These machines are generally given some kind of controller, sometimes source code, to direct their computation. So a virtual machine, in recent literature, is an abstract machine. It has states that represent actual hardware, can be used to simulate hardware on top of actual hardware. So do these ideas apply to a metacompiler? Metacircular evaluator, sort of. In theory, we can interleave translation and execution to interpret at compile time. Self-hosting compiler, maybe in theory we could rebuild C++ itself, but done at compile time might not be performant enough for it to be worth it. And abstract machine, yes, such machines underlie the implementation design. Virtual machine, somewhat, in theory, optimized state transitions can be designed with hardware in mind. Okay, so what then is a metacompiler? It is a tool chain of related technologies which translate source code into assembly. In terms of the technologies that make up this chain, it is the idea of a DSL engine that is most relevant to this talk. So what is a DSL engine? It is an abstract machine which translates domain-specific languages into assembly. So to finish this section, we ask one more question. So we've discussed the idea of a metacompiler more broadly. We ask specifically now, why is C++ a metacompiler? It is so because of its specification, 17 and later. 17 has an emergence of grammar and rules to support a DSL engine, which are also performant. So to make it clear, it is independent of vendor implementation. Okay, so Next section, methodology. So C++ is a metacompiler. We've seen what a metacompiler does. We've seen what a metacompiler is. We now ask how a metacompiler works. To be clear, we are still one section away from discussing implementation. This section offers an overview of the general methods that will be used. Okay, so why talk about methods? A general purpose DSL engine needs to be able to metacompile any language. And so we need its implementation design to be based on expressive theoretical foundations. We start with the methods of compiler theory, which is divided into the front end and back end. I suspect this is a review for a lot of you, but I still want to show that the implementation is based on actual theory. Okay, so the front end focuses on the lexing and parsing of source code. The back end focuses on multi-layered translations from an initial IR assembly to the final target assembly. So lexing, to keep things simple, lexers read source code, translate words into tokens, are constructed from regular languages and regular automata. Parsing, to keep things simple, parsers read tokenized source code, confirm sentence structure, translate sentences into IR assembly, are constructed from context-free grammars and push-down automata. As for backend methods, assembly languages are generally implemented using methods derived from register machines. Such methods coincide well with implementing imperative DSLs. These methods are less effective when implementing functional DSLs. Okay, so we need methods that can implement both imperative and functional languages. To motivate such methods, let's take a quick tour of computing history. So starting with Turing machines, Alan Turing, 1936, equivalent to mu recursive functions, that's the math definition. Well suited for modeling theoretical properties of computable functions, less well suited for modeling practical or performant computable functions. Yeah, so lambda calculus, Alonzo Church, 1930s, equipotent to Turing machines, well suited for modeling theoretical grammar of computable functions, less well suited on its own for modeling certain consistency semantics of computable functions. Lisp programming language next. John McCarthy, late 1950s, influenced by the lambda calculus, is now a family of languages, including Common Lisp, Scheme, Clojure, Racket. Aligns well with the functional programming paradigm. So to delve further into functional programming, we need to equip the lambda calculus, or usually in practice, Lisp, with a type theory. But first, a bit more history. Set theory, Georg Cantor, late 1800s, foundational language of math, proof that there are different sizes of infinity. If taken as a naive theory, it leads to contradictions. Okay, so theory from a math perspective, Bertrand Russell and Alfred North Whitehead, early 1900s. Principia Mathematica, intended as an alternative to set theory. Mathematicians did not adopt this approach, instead vying for axiomatic set theory. But it did help advance the subject of symbolic logic. Okay, type theory from a computing perspective. Multiple contributors, unnamed, mid-1900s, more recently per Martin Loff, late 1900s. Well suited for modeling certain consistency semantics of computable functions. Aligns well with the lambda calculus, functional programming, and the family of Lisps. Okay, so this leads us to abstract machines. We previously introduced this idea, but in the context of the lambda calculus and Lisp, we can specifically mention SE, CD, CE, SK, and Crivline machines. I won't go into their details, I'm just referencing them. Each uses different grammatical artifacts from the untyped lambda calculus to implement its own version of an abstract machine. So abstract machines versus register machines. Abstract machines consist of some version of a control, memory, lookup, and call stack. They transition states by updating these components, which is how they perform their computations. As for register machines, they are abstract machines. The only difference is their design more closely resembles actual computer architecture. Compile time register machines. In this case, I'm actually referencing my previous talk from 2021. It was online. I'm referencing them because my library has foundations, has these as foundations. So they use continuation passing style to transition from state to state. They use template parameters to carry their respective controllers, registers, and call stacks, and use nesting depth counters to implement trampolining as well as prevent recursive closure. Okay, onto the library. So in this section, we finally discuss how to implement a DSL engine in C++. In order to do so, I introduced my CppTMP library. It's an open source repository on GitHub, currently implemented under C++ 17. It does not use the standard library, std. Because of that, last checked, was roughly 20,000 lines of code. Its project status, currently proof of concept, but it's starting to mature and stabilize. In terms of testing, currently it's informal. Otherwise, it's been tested on several laptops, tested using several versions of Ubuntu, compiles under several versions of GCC, including 11.4, compiles under several versions of Clang, including 14.0. Oh.
I was just curious for the reasoning behind why you chose not to use the standard library.
Initially, it was a learning project for me, so I wanted to recreate everything. But then also, if I run into any trouble, at least I can do it myself if I absolutely have to.
Makes sense.
Okay, so if you take a look at the GitHub repository, the major directories are these. So as for the CppTMP directory, it's full of constexpr data structures, a little bit of TMP magic. The assembly directory, it has the continuation machines and DSL engine. Generator directories, it has an LL parser generator. The file put directory, in my project, I need to write my controllers to file. So this part is not constexpr so much. But yeah, it's to write meta object output. So the core directory, that's where I keep the lexer and parser for my core DSL, and hustle directory, lexer and parser for its DSL. Okay, so what about the Metacompiler? We begin with its front end. The implementation is inspired by the Dragon book. Currently, each DSL hand codes its own lexer based on automata theory. An LL parser generator is used to construct transition tables for DSL context-free grammars. This is such an example. It's actually for the hustle language. It's actually nearly identical setup to the Chord and hustle languages themselves. You have a constexpr function, which takes no input. Then there's the context-free grammar. We have a non-terminal representing start. And then you have the various productions, so head and body and everything else. And semantic actions. Okay, so syntax tree implementations inherit from a DSL engine base class. DSL source code translates into meta assembly, which acts as a controller for constructing constexpr functions. As for meta assembly, how does such assembly translate into constexpr functions? We now turn attention back to the Metacompiler backend. So it is designed as an abstract machine, transitioning from state to state. Each state is a triple consisting of a controller, a meta-assembly program which directs control flow, what I call a universe, it's a variadic pack which acts as a memory lookup, what I call a stage, it's a variadic pack which acts as a call stack. So states are implemented using continuation passing style. An example of a continuation passing state. So this is an actual example. I renamed a few things just to simplify, make it look nicer, but than the actual code. But otherwise, you start with a templated struct, which you can specialize so that you can offer names and notes. Notes are just secondary names, but both are numerical indices otherwise. So inside the struct is templated constexpr function. The convention is to call it result every time. So you pass along the assembly parameters. So the C is the controller, the I is the index for where you currently are in the controller. The LT and R are there because every once in a while you do need to do some TMP magic. So I won't go into those details. Okay, otherwise, you have a variadic pack. Okay, so I won't go into that instruction, but basically for these continuation passing machines, each has its own unique instruction. This would be this one's. And then otherwise, it calls the next function. That is actually C preprocessor macros, because like there's nothing special going on there. It's just long-winded to call the next function, so I just hid it away. Oh.
And in the template, the first parameter for the nested template there, assembly params, is that also a macro, or what's going on there exactly?
It is.
Okay. I was like, I don't understand that syntax. Okay.
It's actually just auto C, auto I, auto L. The reason I hide it is it resonates better with the lower part, so like when I'm reading it by hand, it stands out better. Okay. So why continuation passing style? If states are implemented as continuation passing functions, then metaassembly not only controls state transitions, it also constructs a constexpr function along the way. Okay, so refining the backend. It is designed to simulate an abstract machine to achieve compilation. It constructs a sequence of state transitions rather than applying them directly. Although it is not an interpreter, its implementation is still inspired by the structure and interpretation of computer programs, a classic textbook. It's inspired by its metacircular evaluator, which is for the scheme language. Okay, so before we go into the details of how the backend works, it's worth discussing SICPA's metacircular evaluator itself. It is implemented as an abstract machine with each state being a triple. So an expression, an environment, and a call stack. Details. So the expression is the source code being translated and executed. The environment is a list of frames. Each frame is a list of bindings, and a binding is a variable value pair. So it's an associated array. The call stack, it's an expression constructed solely to apply a function to its respective values. Okay, so the crucial process for us to understand is how the call stack environment interact with the source expression being evaluated. With that in mind, I have this illustration. So basically in Scheme, when you're evaluating a program, you start with an empty environment, which has an empty frame. Then you're reading through your program and you're gonna come across like a variable and a value. So you create a new binding, add it to your frame in the environment. You keep going, you'll probably find another one. One of them might be a function definition. So then later at some point you're gonna call that function, in which case you want to create new bindings, but you want to branch them off to the side. Because every function, like it has a signature, like an input, you know, like f at x, so like f at 5, you want to bind the x and the 5. So as you're reading the body of that function for its application, like you might have new bindings, new variable names. At some point, you finish that function call and you return, and then you keep going, you add a new binding, but then maybe you have another function call, branch off again, another function call, branch off again, add a new binding to that secondary function. That finishes, so you finally return to the main line, and then you just keep going, and then the program eventually resolves, assuming it was written correctly. So returning to our Metacompiler abstract machine, let's review its components. Starting with the controller, it is a program composed of metaassembly. It is implemented as an array of instructions. Each instruction is an array of unsigned integers. So what does assembly look like? We saw it once before. So at the moment, each instruction is size 8, but the AN column, that's all the names. The AT columns, that's all the notes. And the numbers are just like parameters you pass to the instruction at the time that it requires. So we now have enough to put some of these ideas together. The Metacompiler frontend uses a SIGPA-style environment to keep track of variables. Instead of keeping track of variables, it holds an index, a promise to where those values will eventually be in the continuation passing universe. So this is why the meta-assembly controller consists of numerical content only. So we next discuss the universe. It is implemented using the left side of a variadic pack. New values are inserted at the end of the left side of that pack. As for the stage, it is implemented using the right side of a variadic pack. New values are pushed to the back of that pack. This has a nice property that argument order is preserved when applying functions to their values when you're building them up. So why use a variadic pack for both the universe and stage? To make it absolutely clear at this point, we are using the same pack that is passed along the continuation machine states. This works because of a correspondence between environment variables, which become indices, and the flat positions within a universe. So this is our previous illustration. But at any given time, you just have like one linear amount of data, and that corresponds to the pack. So when you're applying that function, then you just worry about that line, because like after you finish the call, that data collapses back, and then you can start over and keep going. Same with other functions. Okay, so before we finish this section, we have one last technical issue to address of fundamental importance, recursion. So how do you construct a recursive function from continuation passing style? The trick is to realize we only need call the same continuation machine with the same type data, or typed input. To do this in practice, we only need to keep track of the initial context when defining the recursive function. We then supply that context before the arguments when applying said function. Okay, so this concludes how a metacompiler works in the context of this CCTMP library. Are there any side effects in using continuation machines to implement this? Type checking is deferred until a function is constructed. This means that within DSL source code, literals, variables, and function definitions don't require type info. There's a caveat. Recursive functions are the exception to this because C++ compilers don't like auto-deducing recursive types. And then finally, mutability semantics have an added level of semantic indirection. I'll get back to that a little bit later. Okay, so as for recursive functions requiring type info, it is easy enough to bake the necessary grammar into our DSLs. So this is our chord factorial example again. So that's the type info. This is effectively type name T, like a template parameter, trailing return type. And when you branch, the compiler doesn't like if they don't have matching types, so sometimes you have to specify. Oh.
So it seems like you're letting C++ semantics affect the way you're defining your language by adding that restriction. Would there be any way to have your parser deduce the types for you?
I will mention
your own semantic analysis.
Well, I'll mention that in the roadmap, but one thing I find interesting, well, I come from a math background, so like use math to model other math. So in this case, I'm using C++ as a theoretical model to model other languages, which I find fascinating because they always inherit properties of the languages they're using to model them. But okay. So with the hustle factorial example, same deal, and I even use the same grammar. Okay, so that's the end of that section. Moving on to language section. Sorry, I have to check the time. Okay. This section showcases an inventory of distinct grammars that I have in my code language. It presents some of the expressive potential in using this paradigm of embedded DSLs. So for this one, so we have mutability. basically, my current implementation of the DSL engine, whenever you pass values from C++, it turns them all const by default. So if you want to actually mutate, you have to put a punctuation in front of it. If you don't, the compiler will just say, like, no deal. So this grammar point I think is useful for safety. Okay, so this is a different implementation of factorial. So Chord language is based off assembly, and it's assembly inspired. So I'm going to have goto and labels. Okay, so this language also has very basic function defining grammar. First, you have to declare the variable name, but otherwise, here I'm defining a square function. So I have what I call an argpose operator. It takes one input. Well, it's saying that the function I'm creating will take one input, and then the definition of that function is to multiply the first arg with the first arg, which, if you think about it, is like the square function. Okay, so sum of squares. I first defined the square function like before, but now I have a subpose operator. So it's constructing a function that takes two arguments, and its definition is to add the square of the first argument with the square of the second argument. Okay. Another operator I've added is curry. Just in this case, multiply by 2. But this I find interesting because it wasn't my intention, but it seems like I've recreated lambda captures, but without using actual lambdas. Okay. So I also have a few operators. This is actually the original inspiration for this project, or one of the original inspirations. I was writing a lot of loops that were redundant or like messy. So I came up with the grammar for iterators, and I borrowed it from like functional programming. So you have the classic map operator, which in C++ is transform. But in this case, you can pass any number of iterator input. But with map, you have to use a function to map as you iterate. That grammar, these provide options to the iterators. I'll get into that momentarily. But this one aligns with the output iterator. This one aligns with the input iterator. Okay, so the interval symbols are options which communicate how the functional algorithm acts with regard to iterator endpoints. Sorry. The options are defined as follows. So we have a closed interval, which acts on the left and right endpoints. An opening interval, which skips the left, acts on the right. Open interval, which skips the left, doesn't act on the right. And closing, it acts on the left, not on the right. That's usually the default for most algorithms.
So what does the dot mean?
Like in the code?
Yeah.
Oh, let me bring up another. Okay, so the dot, it's an anonymous variable. And then the line below it, the underscore, it's the same one. I just gave them distinct names to kind of visually clarify which is which, so I don't get confused. But yeah, if you don't want to give an actual variable name, you can just use anonymous. Also, with that said, I'm not actually trying to convince anyone to use my specific grammar here. I'm just showing you that you can pretty much create any one you want, which might be useful for your own use case. But these are for me in my language, and I like them. But I'm biased. But okay. Okay, so I also have a fold operator. In this case, I'm defining sum of numbers. So this fold takes one input iterator. In this case, it has a bit more information. So the fold is an add. The star is not multiplication, it's dereference, because usually when you're working with iterators, you're going to want to dereference. The @ is just identity, so it just says for the for the list, don't dereference or don't do anything. In which case, because I'm doing a sum, I'm taking numbers, and there's no point in dereferencing numbers. Okay, that's the same sort of situation. Okay, so with this, technically I'm calling it an interval, but it's just a fixed interval, just to kind of point out that out doesn't actually iterate anywhere, it just stays the same. But if you're doing a sum, you're going to want to add into that. Okay, so, and then you have the in interval, but this is a closed interval, which with summation you usually want. You want to take the endpoints. So like 1 through 100, you don't want to end up doing 1 through 99. Or okay. So we have another example, dot product. Not going to go into the details of it, but I'm just demonstrating that it's there. And convolution, also fairly straightforward. Aside from everything above and below, you can consider it one line. And you could come up with an entirely different DSL just to optimize for that if you really wanted. Okay, so performance. Performance at this stage of development is informal. With that said, I can still offer some basic stats. So this is C++17 square root Newton's method. This isn't a DSL. It is standard C++17. This is our baseline. So compile times, GCC Clang, like 1/10 of a second. Runtimes, pretty much what you'd expect. Binary sizes, 16K. Pretty much the same for O2 and O3 optimization. Okay, so this is square root Newton's method, but in the Hustle language. This actually, more or less this exact example I borrowed from the Structure Interpretation of Computer Programs textbook. They have it in there. I had to modify it slightly because, yeah, scheme isn't Hustle because you have to do a bit of type, add type info. Okay, so compile times on that, 1.64 seconds. Clang, well, that's GCC. Clang is roughly 3 seconds, 2.982. Runtimes, GCC and Clang, because it compiles into regular C++. Binary sizes, a little bit bigger, 17K rounds to O2 and O3 binary sizes, closer to the baseline. Not quite there, but then again, this is proof of concept. I have not researched optimization. Okay, so also I have a test suite of 20 chord functions. I won't show them here. They're all small, kind of similar to what I've shown. But metacompiling all these at once, we get GCC would compile them in 4 seconds, well, 4.1 seconds. Clang, 9 seconds. Runtimes, it's just standard C++. Binary sizes, again, quite small. Okay, so roadmap. So as previously stated, this project and its library are still proof of concept. As such, and to wind down this talk, I offer a roadmap for future directions. Thing to note is that for as much as this paradigm is stabilizing, there are still open areas of research. I'm willing to say the main reason for this is because of the self-similarity of these designs. The self-similarity creates what I would call a two-tier system. The first tier is C++ itself. It has a first tier type system and mutability semantics. That's some of the issue you brought up. Okay, so the second tier is any given DSL which can potentially have their own type systems, mutability semantics, etc. So for example, the C++ compiler offers error messages, but what about the DSLs? Currently they do not, but they will. What's more, you can design for their inclusion the same way you would for any compiler. Also, as there's very little TMP magic in this library, and given that the continuation machines have a step-by-step nature, this means that errors at their level are relatively easy to track. In any case, I want to say that this two-tier system has some benefits in its design. Notably, it mitigates the learning curve for anyone exploring this paradigm. For example, there may be some new details, but if you already know how assembly works, then meta-assembly is largely the same. With that said, everything has a trade-off, and there are some disadvantages as well. In the realm of context switching, names matter. This is to prevent confusion and general misunderstanding. To use assembly again as an example again, if you say the word assembly, do you mean hardware or continuation machine? As for open areas of research, I offer the two-tier type system as an example. So Metacompiler DSLs are deferentially typed, which is they are statically typed, but for type checking until the constexpr function is built. What if we want our DSL to have a complete type system of its own? How best to negotiate between the tiers? So the two-tier type system, continuation machines potentially introduce DSL undefined behavior. So DSL variables are untyped, and so you can assign new values to different types to these variables. What safeguards should we set if you don't want that, and how best to do it? So this paradigm introduces the possibility of reifying meta-assembly. Do we create a second tier of data structures specific to DSL languages? How should they interoperate with compile time C++ more generally? As for the roadmap, the first step is to finish implementing the Hustle language. For example, the following code does not yet work. Notably, basically it's dispatches on addition, multiplication for the numbers 2 and 3. But more generally, the roadmap is as follows. So I use the Hustle and Chord DSLs to re-implement the CCT library to become semi-self-hosting. I use this semi-self-hosting library to prototype and recreate better versions of itself. Extend this library to include a lexer generator, a LR parser generator, a data structure generator. I use this extended library to research and resolve open problems. Finally, I'll add, I have no ideal timeline for solving the open problems, but I'm hoping to code the semi-self-hosting library with extensions within a year. That's the end. Thank you. Any questions? No.
So I guess I don't understand what you mean by semi-self-hosting.
Well, it's kind of a technicality because, like, if I wanted to make it self-hosting, all of this technically is C++.
Right.
So technically, I'd have to make C++ self-hosting, and that's too big of a job for me. But with my DSL library, I can recreate parts of it that I originally used to create it.
Okay.
And then just reduce the code size and stabilize it.
So I walked in 2 minutes late, so I'm sorry if you already addressed this. But I think this is like really, really cool as a proof of concept. Like, it's awesome to show what can be done at compile time in C++. And I'm 100% all for science for its own sake. Like, I've got tons of projects that I've done just because I want to see if I can do something. But I was just wondering, in terms of concrete use cases, what were you originally targeting this at?
I plan on making my own multimedia programming language. I'm going to use C++ to do it, but for me, I want to build a library of tools to make that easier.
Cool. Thank you.
Any other questions?
You had a slide that had the context-free grammar for one of the languages. Does that go into a compile time parser generator for the language?
Yes. In the long run, I would like to rewrite that. It was my very first one, and it's very messy, but as I build more tools, I can probably use those to rebuild that itself as well as part of the semi-self-hosting design. Okay. Thank you.